Discrete Fourier transform. We have talked about discrete time Fourier transform. That is discrete time Fourier transform. With the discrete time Fourier transform, here's the definition. Summation over n. This is a discrete time Fourier transform, and we may plot this discrete time Fourier transform. It is periodic 2 pi. Suppose this is the plot, and this is y, e, j, omega. It has a period of 2 pi. And this y, e, j, omega, it's actually a function of omega. It's a function of continuous variable. Continuous variable. Omega. It's a function of continuous variable omega. In many applications, we need to look at the discrete time Fourier transform plot. And the purpose could be for design, the purpose could be for analysis. For various reasons, we would like to look at the plot of a discrete time Fourier transform. And we would like a computer to generate such a plot for us. A plot that, for example, in this example, the Fourier transform of y, e, j, omega look like this. We would like to see such a plot. How can computer generate a plot like this for us? Is it possible that the computer can evaluate or compute the discrete time Fourier transform y, e, j, omega for every omega? For every omega between 0 and 2 pi. Is it possible for the computer to do this? Is it possible to compute y, e, j, omega for all omega, for every omega in the period 0 to 2 pi? Can we ask the computer to evaluate y, e, j, omega for all omega in this range? First, maybe we can ask how many omega are there between the 0 to 2 pi range? There are infinitely many omega in this range. It's not even countable. So it's not possible for computer to compute y, e, j, omega for all omega between 0 and 2 pi. So what would be a more practical approach? Because nowadays we rely on the computer to give us plot of Fourier transform routinely. We use the computer to generate plot for discrete time Fourier transform all the time. So how does computer do it? What it does is that it samples. It samples the discrete time Fourier transform. Because omega is a continuous variable, and we may sample. Suppose we divide the 0 to 2 pi into n parts. And each part is 2 pi over n, and continue on like this. And we sample, we take a sample every 2 pi over n. We take a sample every 2 pi over n. And how many points do we have? How many points do we sample now? Because we divided into n parts, right? So we would have n points. And these samples are what we call discrete Fourier transform. The endpoint DFT, we use the notation YK. That is the samples of the discrete time Fourier transform sampled at 2 2 pi over n k times. And the k goes from 0, 1 to n minus 1. Y0 is the Fourier transform. Evaluate at the DC frequency. Y1 is the Fourier transform. Evaluate at 2 pi over n if it's an endpoint DFT, and continue on like this. Y n minus 1 is the Fourier transform evaluated at 2 pi over n minus 1. If we plot the DFT, it will be a sequence of endpoints. Value of the samples would be simply what we have here. What we have here, 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 here. Okay? So now we can plot here the first sample, second sample, continue on like this. So they will be the samples of the discrete time Fourier transform. The names are actually quite similar. One is discrete Fourier transform, and the other one is discrete time Fourier transform. In discrete time Fourier transform, we mean this is the Fourier transform of a discrete time sequence. So this discrete means discrete time. Discrete as in discrete time sequence. But in discrete Fourier transform, this discrete means that it's discrete in frequency. This is discrete in frequency. So both of them has the discrete in the name, but the meaning is a little bit different. So one is discrete time Fourier transform. It's the Fourier transform of a discrete time sequence. And the other one is discrete Fourier transform. This discrete means it's discrete in frequency, because now we samples. And when we take samples, the samples will be at discrete frequency instead of a function of continuous variable omega. So discrete Fourier transforms is simply obtained by sampling the discrete time Fourier transform. That sounds awfully simple, doesn't it? So what is there to talk about in this whole chapter? Well, there's a lot to talk about. Earlier we talked about some property of discrete time Fourier transform, but now we know whenever we look at the computer plot, it's given in DFT. And we need to know how those discrete time Fourier transform properties would translate in DFT. First of all, we know from a discrete time sequence, we can compute the discrete time Fourier transform. And from the discrete time Fourier transform, we can also compute the discrete time sequence. So the error goes both ways. One side from this direction is discrete time Fourier transform, and the other direction is inverse discrete time Fourier transform. And just now we mentioned the definition of a endpoint DFT. From a sequence, we can compute the DFT. Oh, notice that we have used the same notation y ej omega. Y ej omega as discrete time Fourier transform, and yk as DFT. So whether this means the discrete time Fourier transform or the DFT, you have to look at the argument. If it's ej omega, then it's the discrete time Fourier transform, and if it's a k, an index k, then it's the DFT. So from the yn, we can compute the DFT yk. Does the error go the other way too? Is it possible to obtain back, to compute back yn from the DFT? So this is the first thing that we would like to answer here. The secondly, there are actually many properties of discrete time Fourier transform. And now we would like to talk about the analogous properties in DFT. And then also one thing when we talked about the inverse DFT, this is inverse DFT. After we talked about inverse DFT, there's something that's called discrete Fourier series that we would like to mention their connection with discrete Fourier series. Okay, discrete Fourier series is the discrete version of the Fourier series that you have learned for continuous time signals. So here are some of the issues that we will talk about in this chapter. So first we would like to answer the question, is it possible to obtain the sequence Yn if we are given its endpoint DFT? Suppose the sequence Yn is a sequence of length n, and its endpoint DFT will simply be n goes from 0 to n minus 1. It has only n samples, and e minus j 2 pi over n. In the place of omega, we will put 2 pi over n k, and then n. Okay, so this is the endpoint DFT. K goes from 0, 1 to n minus 1. So there are actually how many equations here? For each k, we have an equation. So there are actually a total of n equations. And that's how the endpoint DFT is related to the sequence Yn. Let's write down the n equations to take a close look at how Yn and Yk are related, and then perhaps we can answer the question of whether or not it's possible to get Yn back from its DFT sequence. When we write down these n equations, this exponential term is a little bit cumbersome, so let's try to simplify the notation somewhat by define a new notation called W. This W is equal to e minus j 2 pi over n. We let W to be this quantity. This is a scalar. This is simply a scalar with a unit absolute value. And with this new notation, we can simplify the equation for this DFT. This becomes 0 to n minus 1, Yn, and then W, because this minus 2 pi over n is now in W, so this exponential term is Kn. And again, k goes from 0, 1 to n minus 1. Now let's write down the n equations. When k is equal to 0, we have a y0, and y0 is equal to, this is summation. This is summation here. There are n terms here, and let's write down each term separately. N equal to 0, we have a y0, and w raised to the power of 0, that will be 1, and then y0, and then y1, n equal to 1. When we plug in k equal to 0, k equal to 0, and n equal to 1, we still get a 0 exponent. So this is the whole term is still 1. We'll continue on because k is equal to 0, so the exponential term just disappear, and then we get y m minus 1. That's the case when k equal to 0. When k is equal to 1, y0, we still have a y0, k equal to 1 and n equal to 0, so the exponential term still disappear, and then y1, now k equal to 1 and n equal to 1. Then we get w raised to the power of 1. Then continue on like this. We get y n minus 1, and then w raised to the power of k equal to 1 and n equal to big N minus 1. We get n minus 1 at the exponent. Now k equal to 2, continue on like this. N equal to 0, we still get 0. And then y1, k equal to 2, to n equal to 1, we get w raised to the power of 2, y n minus 1, n equal to n minus 1, and k equal to 2, so we get 2, and then n minus 1. We continue on like this, all the way to k equal to n minus 1. Then we get y0 plus y1, and then w raised to power kn, right? K is equal now, is now n minus 1. Then continue on, y n minus 1, and k equal to n minus 1. This is k, and then n also equal to n minus 1. Now there we go. We have n equations. So this is a system of n equations. Now let's look at these n equations. We can put these n equation into one big equation. How can we do that? We can put all the DFT samples into one big vector of length n. Here we go. This is a big N instead of small n. This is a big N. This is a big N. Now we collect all these equations into one. We collect all these DFT samples into one big vector. And we call this vector y. Now let's write down these big equations. We can collect all these n equations together, and we can write it in a matrix vector product. As we can see, each equation is actually a linear combination of the time domain samples y0, y1 to yn minus 1. We can see that for the equations, each equation is a linear combination of y0, y1 to yn minus 1, and the second equation also a linear combination y0, y1 to yn minus 1, and every equation is a linear combination of y0, y1 to yn minus 1. So each DFT point is a linear combination of y0, y1 to yn minus 1. y0 is simply y1, 1, all the way 1. And y1 is 1, and the second coefficient will be this coefficient here, this coefficient here. So it's w1, and the next coefficient all the way to the coefficient of a yn minus 1 is wn minus 1. So let's put wn minus 1 here. And continue on yn minus 1. If we want to look at yn minus 1, the coefficient for y0 is 1, and then it's wn minus 1 all the way to wn minus 1 and minus 1. So the coefficient for small y0 is 1, and then it's wn minus 1, and then all the way down to wn minus 1 and minus 1. Now we have a system of n equations written in the form of a matrix vector product. We call this vector big Y, and this vector small y, we put an underbar to indicate that this is a vector. Same here, this is a vector n by 1 vector, and this is also a n by 1 vector. And this thing in between here is a matrix, and we will call this matrix W matrix, and has an underbar. is different from the scalar W because it's an underbar. And this matrix has dimension. What's the dimension here? The dimension here will be n by n. And W has a name. It's called DFT matrix. It's n by n DFT matrix. Why is it called DFT matrix? Because if we are given this small y vector, we're given this vector here, and we multiply it with this matrix W, then we get its DFT, endpoint DFT. So big Y is equal to W, the product of W and Y, the matrix and the vector product. So if we apply W matrix on small y, then we get its DFT. So that's why it's called the DFT matrix. Now going back to the question of, is it possible to obtain Yn from Yk? Is it possible if we are given the DFT samples? Is it possible to get back Yn? We can now pose this question in a different way. In this big Y equal to W times small y notation here, the question can be recast as, given the big Y vector, n by 1 vector, can we get back small y? Suppose I tell you the big Y, can we obtain the small y? So what kind of question is this? This becomes a linear algebra problem. Given this y vector here, can we get the small y back? It really depends on this W matrix, doesn't it? It is possible. Yes, it is possible we can get back a y. Yes, but there's a condition, right? There's a condition. What is the condition? What property does W have to have if W is invertible? So is W invertible or not? Let's examine this DFT matrix and see what kind of property does it have, and is it invertible or not. Now let's look at DFT matrix more closely. For example, n equal to 4, then we have a 4 by 4 DFT matrix. And this is what a 4 by 4 DFT matrix look like. 1, 1, 1, 1, 1, 1, 1, and then W squared, W raised to the power of third, W squared, W4, W6, W third, W6, and then W9. So that's what a 4 by 4 DFT matrix look like. It's actually quite regular. We can see that it has some special property here. This type of matrix look kind of familiar, doesn't it? Doesn't it look familiar? I'm sure that you might have seen matrices like this in high school. There's a special name for such a matrix. Does it ring a bell? If it doesn't, if I write it in a different form, I'm sure you will recognize it. Suppose I have a matrix. It's on this form. It's 1 alpha 1 alpha 1 square. And then for the next row, it's 1 and then alpha 2 and then alpha 2 square. And 1 and alpha 3 and alpha 3 square. A matrix like this. Does it look familiar? This is called Van der Waals matrix, and it has a very beautiful property when it comes to its determinant. Its determinant is simply alpha 2 minus alpha 1, alpha 3 minus alpha 1, and alpha 3 minus alpha 2. That's the determinant. And from this determinant, we can see whether its determinant V. And we can see whether or not this matrix is non-singular, is invertible or non-singular or not. It's a invertible matrix if all these alphas are distinct. It's non-zero, where this V is invertible if alpha 2 and alpha 3 are distinct. That means they are all different. That is alpha I not equal to alpha j for I not equal to j. Then we say they are distinct. Okay. Now let's go back to our DFT matrix. I think I have lost a R here. How come I have lost an R? My Vanderman. It has an R here, Vanderman. Now let's go back to the DFT matrix. Is our DFT matrix a Vanderman matrix? Yes, indeed. And what is our alpha? This would be our alpha 1, and that would be our alpha 2, and alpha 3, and then alpha 4. And our DFT matrix would be invertible if all these alpha are distinct. And indeed, they are all distinct, right? Because these alphas are 1 and W squared and W raised to the power of third. They are all different. So indeed, it's invertible. This W is a Vandermonde. It's a Vandermonde matrix, and it's invertible. So W inverse exists. Returning to the problem that we posed earlier, y is equal to W and then small y. Now that W inverse exists, we can simply multiply W inverse on both sides. Then we get y equal to W inverse y, small y. So that's no problem. But it turns out that this W, it has this very special property that its inverse can be written in a very nice form. So let's take a deeper look at this W matrix and see how from this small y we can obtain the big Y vector. W is n by n. Let's write this n by n matrix in terms of its vectors. We have a small w, 0, the first vector, w1 vector, this next vector, and then wn minus 1. These are the column vectors of w. This wn column vector, the nth column vector of a big W matrix, it's simply 1, and then wn, this is a scalar n, scalar w, and then wn minus 1, and then n. Okay, so this is the nth column of W. Now let's take the Hermitian of this vector here. Let me first define Hermitian. If we have a matrix that is n by n, then the Hermitian, we use the notation A Hermitian, is simply a transpose and conjugate. Transpose and conjugate of A. So for example, A Hermitian would be a n by m matrix. For example, A is a matrix like this, 1, 0, 0, J, and then 1 plus J, and 1, then A Hermitian, underbar to indicate it's a matrix. A Hermitian would be a 3 by 2 matrix, and the first column would be 1, and then 0, and 1 minus J is the conjugate of this one. And the second column would be the second row of A, will correspond to the second row of A, 0, minus J, and then 1. So that's transpose and conjugate. Why do we talk about transpose and conjugate? Because now, if we take the transpose and conjugate of Wn, Hermitian, and we multiply with Wn, then what do we get? We get 1 W minus N, W minus M minus 1N, and the W vector is 1 Wn, Wn minus 1N. Oh, let's take the Hermitian of M. Yeah, let's make it more general. Let's take the Hermitian of Wm. Wm here. So this one is M, and this one is M. What does the product amount to? If we multiply the first term by first term, we get 1, and then the second term together we get N minus M, and the following term will be W M minus M under 2 all the way to W N minus 1, and then small n minus small m. What kind of series do we have here? It's a geometric series, isn't it? It's a geometric series with a common ratio W and W raised to the power of n minus m. Now, when n is equal to m, then W m minus m would simply be W raised to the power of 0, and that's 1. So each term is 1. So we get n term, then we get n. When n is not equal to m, we can use the geometrical series with a common ratio W raised to the power n minus m to write down a general expression for this summation here. The common ratio is W n minus m. Oh, this is n not equal to m. M minus m. At the numerator, we have 1 minus W n minus m. And how many terms are there? There are a total of n terms. What does this mean? Let's look at the numerator again. The numerator contains the term n minus m and then n. What is this one? Remember, W is equal to minus 2 pi n. If we have n minus m and then n, then what do we have here? This n and this n will cross out, and we get e minus j 2 pi n minus m. What is this thing? It will be an integer multiple of 2 pi, right? So this is actually equal to 1. So we have a 1 here, we have a 1 here, and this one is also 1. 1 minus 1, we get a 0. In other words, this is equal to n when n is equal to m, and this is 0, when n is not equal to m. This is Wm emission Wn. What does this mean? What does this equation tell us about the column vector of the DFT matrix? This means the column vectors of the DFT matrix are actually, there's a name for this. They are orthogonal. So these column vectors, they are orthogonal. And that will make the DFT matrix a orthogonal matrix. This means that the DFT matrix is orthogonal matrix. And for orthogonal matrices, their inverse are very easy to find. In particular, if we take the transpose conjugate FW, then we get the column vectors becomes the row vectors with a transpose and conjugate. We get W0 Hermitian, W1 Hermitian, all the way to Wn minus 1 Hermitian. If we multiply W Hermitian and the W together, we get W0 Hermitian all the way to Wn minus 1 Hermitian, and then W0 to Wn minus 1. If we multiply out, then we get, for the first element, it will be W0 Hermitian, W0. For the second element, it will be W1 Hermitian, W0. So this is a scalar. And then this is a Wn minus 1 Hermitian, a row vector, and a column vector. This is again a scalar. And continue on like this. We get W0 Hermitian, a row vector, and Wn minus 1. And here we have Wn minus 1 Hermitian and Wn minus 1. Okay? Each element is the product of a row vector and a column vector, like this. And if we look at the elements of this product, this is W Hermitian W matrix here. How many non-zero elements are there? Where are the non-zero elements? It would simply be if it's a diagonal element, like this one, then we know that corresponds to the case that m is equal to n equal to 0, and m equal to 0. When n equal to m, this is equal to n. So that would be a n here. And for all the other elements, W1 Hermitian W0, then we get a 0 here. So for all the other elements in the first column, we get 0. So we get 0, 0. And then for the second column, we can see that only the diagonal element, we get a n. We get n at the diagonal. We get n here, and for all the others, we get 0, 0, like this. So in the end, what do we get? What kind of matrix is this? This is a diagonal element with n on the diagonal. So we get n times identity matrix. Identity matrix. Now what's the conclusion here? We get W Hermitian W matrix equal to n times identity matrix. So can we determine the inverse of W? The inverse of W will simply be W inverse will simply be related to W Hermitian, right? But only there's an extra 1 over n. What does this mean? Is it easy to get W inverse? We know from linear algebra, given a matrix to compute its inverse, it's not so easy a task. You have the methodology to compute it, but then it involves some computations. But with a DFT matrix, because it's orthogonal, so how can we compute the inverse? We don't really need to do anything, right? We just simply take the transpose and conjugate of W, and whether this is scalar n, then we get W inverse. No computation. Now that we have obtained this is W inverse, this is a small y, right? Small y, and this is big Y. This is small y is equal to W inverse and then big Y here. Okay, now that we have W inverse, we can use W inverse here and apply it on the big Y vector to get back the small y vector. Now we can use the DFT inverse to get back the small y. And small y vector is W inverse big Y vector, and this is equal to 1 over n W Hermitian and then the big Y vector. Now we can plug in this matrix W Hermitian and write down the details of this equation. The nth element of the small y vector is yn, and then it would be, if we evaluate the matrix vector product, it would be W Hermitian, the kth element, and then yk. That will be the kth element of the big Y vector. K goes from 0 to n minus 1, and there's still n 1 over n scalar. Let's not forget that. And the W Hermitian nk element, because it is the conjugate and transpose of W, so it will be the W matrix Kn element, and then with a conjugate yk. K goes from 0 to n minus 1. This is equal to 1 over n. K from 0 to n minus 1. And then W Kn. Because there's a conjugate, so we have a minus sign. Remember, W is E minus J 2 pi over N, right? And this is YK. Or we can write it in its original form, the exponential term. E J 2 pi over N, Kn, and then yk. That's the inverse DFT. So with the IDFT, we can compute yn from the DFT sequence. Ej 2 pi over n, Kn, yk, K from 0 to n minus 1, 1 over n, and the DFT will compute yn the DFT sequence, and the K goes from 0, 1 to n minus 1, and n goes from 0, 1 to n minus 1. So this is the DFT and the IDFT. And what this means is that if we have a sequence yk, it has endpoint 0 to n minus 1. This is n, yn. From the yn, we can compute its dtft, yej omega. This is 0, and this is 2 pi, and this is omega. There's a one-to-one correspondence. From the Yn sequence, we can compute the Dft Yej omega. And we can samples. In this case, because Yn is an endpoint sequence, we can take samples of the discrete time Fourier transform. And suppose we take n samples, and here are the n samples. The n samples are called the DFT. This is the DFT sequence. The DFT sequence corresponds to the samples. 0, 1, 2, n minus 1. And there's also a one-to-one correspondence. From the time domain sequence, we can compute the DFT, and from the DFT, from the endpoint DFT, we can also get back the time domain sequence. So the interesting thing, we know from the time domain sequence, we get the discrete time Fourier transform, right? And the discrete time Fourier transform is a function of a continuous variable omega. And from the discrete time Fourier transform, we know the function for every omega. The function for every omega, then we can get back the time domain sequence. But now there's something, the thing that's interesting here is that if Yn is a sequence of endpoint, 0 to n minus 1, now we don't need to know the whole discrete time Fourier transform for every omega. For every omega, we don't need to do that. We can get back Yn if we just take samples of the discrete time Fourier transform. We take n samples from the discrete time Fourier transform, we get the DFT, and still with these endpoint DFT, we can get back the discrete time sequence. Isn't that pretty?